Like almost everybody made it back from their hike. Only a few people are still lost up on the slopes or wherever they've gone. I sat down to just do a couple revisions to slides, and then I started thinking about it. I've been having fun talking about biology with John here, and so I actually added a few slides on the UV part and ozone, which was at the end of the last lecture. And I'll probably then run out of time on hydrogen escape. But I figured that's probably, you all won't mind that much because that's sort of a mathematical bit going through how hydrogen escapes from the Earth. And the last part of it is not really that necessary. So if we don't get there, that's fine. And there's some fun stuff to talk about with ozone and UV screens back in the Archean. So let me pick up then where I left off. We was talking about the rise of oxygen this morning, and something that goes right along with that is the rise of ozone, because ozone is produced photochemically from oxygen, and ozone is very important in the modern world. Of course, we worry about it a lot. We were busily destroying the ozone layer up until about 15 or 20 years ago, and because we were putting a lot of freons into the atmosphere, and the chlorine was having harmful effects on ozone. Ozone has also been UV shielding has been an issue for the early Earth. And it's kind of a controversial issue. In fact, it's funny, this goes back to a debate that went on between Carl Sagan and Lynn Margulis in the literature. Some of you may know Carl was married to Lynn for a short time, and maybe part of their problem was they didn't agree about the effects of solar ultraviolet back in the Archean.
I would do it.
So Carl was a physicist and an astronomer, and he thought that UV was really important, and that early life would have been in bad trouble because of it. And Lynn was a biologist, and she was convinced that the early organisms really could care less, mainly because they would form mats and they would hide under each other's dead bodies, and so it was not a big issue. If you had free-floating phytoplankton in the oceans, it probably would have been an issue for them, because they get brought up to the surface and would be exposed to any UV flux that was coming down there. So let's think about these early organisms for a little bit, and John, maybe I'll impinge on what you're going to talk about, but it seems to be okay if we overlap.
I'm not going to talk about this, but I have some comments on it for sure.
Oh, okay. Well, let me say a couple things, and then I'll let you chime in. A lot of the early organisms lived in mats, and of course, we're prejudiced on that because the ones that we can see a record of best are the ones that lived in mats. We think they formed these structures called stromatolites, which are layered deposits in rocks that are thought to be the remnants of microbial mats. This is a domical stromatolite here, or a conical stromatolite, and here's a layered one right here. These are from the 3.5 billion year old Warrawoona Formation in Australia, and these slides were given to me by Bill Schopp at UCLA. Bill argued for many years that these were probably the remnants of cyanobacteria, and so that I grew up scientifically believing that there were cyanobacteria at 3.5 billion years ago producing free O2. Now, since that time, the evidence for cyanobacteria at 3.5 billion years has been questioned. And so actually I'm skeptical that these were cyanobacteria mats, but they were probably some kind of photosynthetic organism because they lived on the surface, they were phototactic, and they were probably one of these anoxygenic photosynthetic type of organisms that I've talked a little bit about and that I think John is going to talk about more. And John, I'll show a couple more of these. These are sometimes called living stromatolites. This is Shark Bay in Western Australia, And these are cyanobacterial. They're not really mats so much as they are columns. They're in the subtidal region where the tide goes in and out, and they trap sediment and form these structures. They only live in restricted areas of the Earth today because in most places they get eaten by fish, particularly parrotfish. If you've ever been to a coral reef, there are these fish there with parrot-like beaks that eat on the reefs. And so these mats would be, they get eaten everywhere. But Shark Bay is very special. It's a restricted inlet, and it's, I think, 3 times ocean salinity in there. So it keeps the parrotfish out and allows these microbial structures to grow. Back in the Archean and the Proterozoic, all the way up to the Cambrian explosion, there was nothing like a parrotfish. In fact, until the Ordovician, fish didn't come along, and so these structures were all over the place, presumably, and a lot of them are preserved in the geologic record. And maybe, John, did you want to say something at this point? Okay, so anyway, these organisms may or may not care about UV because they form these structures, and the living ones could be underneath the dead ones there, which was always Lynn Margulis's.
Okay, I will make a point then, because the cyanobacteria, as do virtually all photosynthetic organisms that use light in the 400 more visible range, so they're not deep down, produce a lot of accessory pigments, including carotenoids and others, that actually do help absorb UV. Secondly, one of the really most universal and very early on, I think after photosynthesis came along in particular, a whole set of genes that we call stress stimulons became universal in all 3 domains of life, basically. And these are to deal with the stresses that come with, for example, oxygen radicals, UV, etc., and all the stresses. The cyanos are fully equipped with all of that. So I just thought I'd mention.
So that would imply that they were stressed by UV?
Oh, yeah, absolutely. In fact, everything was. And there's a whole set of very ancient enzymes that we call, that are involved in DNA repair, and it's called the SOS response.
Okay, well, in that case, I'm already set up to be contradicted on what my next slide is. So my next slide is, don't forget about the organic haze layer that I said might be there. Carl Sagan, this is another one of Carl Sagan's ideas. He wrote a paper, actually Chris Chiba, one of his students, wrote a paper with Carl that came out after Carl's death, where they suggested that they were aware that you could form organic haze from photolysing methane, and Carl always wanted to try to keep ammonia alive on the early Earth. So he and Chris Chiba suggested that haze layer that you create from methane photolysis could have shielded the ammonia and kept ammonia around as well. And actually, if that was right, then this haze might have provided at least.
I think the haze was really important. I mean, anything that can actually hold out UV is great. I mean, the carotenoids will do something for you, and you don't want to use your repair mechanisms unless you have to.
Mm-hmm. Well, the haze has gotten better just in the last year or so, and there's a problem. If the haze gets too thick in the visible, then you get this anti-greenhouse effect that cools the surface, and so it's self-limiting. If it gets too cool, then that kills off the methanogens that are producing the methane, and so the haze optical depth in the visible can never get more than a few tenths or so. And in the old models, our old models of haze, and just about everybody's old models of haze, that was then too little to give you a very good UV screen. But there was a new paper that came out by Eric Wolf and Brian Toon at University of Colorado. Brian is a former Carl Sagan student himself. And what they showed, they were looking, Brian works a lot on Titan, and the people studying Titan have been studying that haze very carefully in order to interpret Cassini measurements, and in particular to get the right albedo spectrum from Titan. And what they find is that they can reproduce the optical properties of Titan much better if they assume that the haze has a fractal shape instead of little spheres. And that sounds confusing at first, but think about it. These are little hydrocarbon particles. They're formed from polyacetylenes, we think, and they're more like carbon snowflakes than they are like spheres. They're certainly not spherical. Those of you who do scattering theory know that the only way we really know how to do scattering theory is with spheres. So it's called me theory. And so how do you treat something that looks like a snowflake using me theory? Well, what the Titan people have been doing is they assume that fractals are shapes that repeat on smaller sizes. And so they make their Hares particles out of like a big particle that's a big sphere that consists of many smaller spheres, thousands of smaller spheres that are part of it. And so it mimics the effect of this sort of fine structure that a snowflake would have. And the net result of that is that the small particles interact most strongly with wavelengths of light that are comparable to the particle size itself. And so these small particles in the fractal haze interact very strongly with UV light, and they give you a much better UV screen than you get from just spherical particles. So here's a figure from their paper which shows the haze optical depth. This is wavelength in microns, so the visible is 0.4 to 0.7, and the UV is down here below 0.3 in these units. Ammonia absorbs shortward of 230 nanometers or 0.23 microns. And notice that in this particular model, the optical depth of spherical haze particles is more or less uniform. It increases slightly towards the UV, but these fractal particles go way up. And so what that means is that if this is right, then you can have an optically thin organic haze in the visible, so you don't get too much anti-greenhouse effect, but it can provide a much better UV screen than we had thought was possible. And that may or may not be important for early organisms, and also it does revive the ammonia idea a little bit, although you still have to have a source for ammonia, and the sources for ammonia are not as big as Carl Sagan probably would have liked. So anyway, that's sort of an aside. Ozone is important, and once oxygen went up at 2.4 billion years, then the ozone layer would have started to develop. And one of the questions that's been looked at actually by 7 or 8 groups over the last 30 years is how fast would the ozone layer develop as you put oxygen into the atmosphere. These are some calculations that were done by a former postdoc of mine, Antigona Segura, several years ago. And what she did is she ran coupled photochemical climate calculations. So she was running back and forth between a 1D photochemical model of the atmosphere and a 1D radiative convective model. With the photochemistry, she could calculate ozone profiles here, ozone number density as a function of altitude for different oxygen levels. So that red curve at the right is for 1 PAL of O2, present oxygen, and then for taking out successive factors of 10 of the oxygen. And you can see the ozone layer goes away as you take out the oxygen. And then on the right are temperature profiles that are done by iterating back and forth. And today, of course, you get this big warming bulge in the stratosphere that's due to the absorption of UV radiation by the ozone. As you take out the ozone, then that temperature bulge disappears, and so by the time, or as you take out the oxygen, by the time you're down to about 1% of present oxygen, the stratosphere is more or less isothermal. Now, what is important for the UV at the surface is the column depth of ozone, the amount of ozone between you and the sun. So you can plot that for, these are actually some older calculations here, but they're not very different. These are from a 1985 model that I did, and the chemistry hasn't changed that much since then. So I think the solid curve here was my 1985 results, and compared with some dash curves that were some previous models by myself and by Joel Levine. And what you see here is that the ozone is the nonlinear function of oxygen. And this was actually not a new result either. There was a little analytical model done by Ratner and Walker back in 1972 that showed that it was nonlinear. And furthermore, notice that the ozone actually turns over as you go to higher oxygen. It doesn't just continue to increase. The reason is you have to think about how ozone forms. The way you form it is you photolize O2 and make oxygen atoms, and then O plus O2 plus a third body goes to ozone. You need that third body to take off the excess energy of the collision so that the O and the O2 will stick together. Well, the more oxygen you get, the higher the ozone layer moves up, or the higher the absorption by O2 moves up in the atmosphere, and the number of third bodies decreases because the pressure is going down up there. So conversely, when you take out the oxygen, the ozone doesn't go away that fast because the UV just simply penetrates deeper into the atmosphere, photolizes O2, and then you got more third bodies around in order to make the ozone. So that means that in these calculations, there have been different definitions of what's an effective screen for biology, but one particular definition, in fact, two particular definitions right here. I think one of these was from Bertner and Marshall's papers, and the other was from Ratner and Walker, I believe. It looks like at something a little over 1% of present oxygen, you would have an effective ozone screen. Now, when oxygen goes up at 2.4 billion years, it almost certainly goes up above 1% of present oxygen. So that implies that the ozone screen was established at the same time that oxygen went up. And there was good ozone shielding all the way through the Proterozoic. Now, the other reason I stuck this in here was because Elaine Leger has worked on this problem too, and Elaine has thought about it from a different context. You know, Elaine worked for many years on the Darwin project to image planets in the infrared around, planets around other stars, and do that in the infrared and look for biosignatures there, including that of ozone. Ozone has that strong 9.6 micron band in the infrared, which is the ozone molecule doing like this. Well, Elaine pointed out in a paper back in 1993, you had noticed the nonlinearity here, and you get even more nonlinearity in the spectral signal because the depth of a signal here is proportional to the amount of absorber, ozone in this case, and also the temperature difference between the surface and the absorbing layer. And what happens is you take the ozone out of the atmosphere, that stratosphere is cooling, whereas the surface is staying warm. And so you actually get a deeper feature. And this on the left, this is the oxygen feature in the visible, or in the near infrared at 0.76 microns. This is another thing that with a visible and optical version of terrestrial planet finder, we would look for this signal. Notice that this bottom curve here is for 1 PAL of oxygen. This is radiance, a radiance plot here. So for 1 PAL of oxygen, you get a really nice deep oxygen band there. When you take out a factor of 10 of the oxygen, a lot of that goes away, and by the time you're down to 1% oxygen, it's pretty flat. The oxygen signal has disappeared. But you look in the ozone here, and this is the same result I think that Elaine showed in his paper. The ozone band for 1 PAL, 10 to the minus 1, and 10 to the minus 2 basically lies right on top of each other. And then it starts to go away here at 10 to the minus 3 PAL of oxygen, and it's flat below that. So what that means is if you suppose, we don't know what oxygen was in the Proterozoic, but it was probably somewhere between, that's that period of time between 2.4 and 0.6 billion years ago. It's about a third of the Earth's history. We don't know what ozone or what oxygen was there, but it may have been in the range of 1 to 10% of present. Well, you'd have a hard time seeing that if you looked in the visible here, because that oxygen signal is pretty small. But the ozone band, if you flew something like Darwin, would be sitting there and staring you in the face. And so it's really a very good bioindicator. It's a better indicator of oxygen than oxygen itself is, if you think about it from a spectroscopic standpoint. All right, so let me leave you with some conclusions here. This applies to the oxygen talk as well. Oxygen was low before 2.4 billion years ago. We all agree that cyanobacteria produced that oxygen. What I've just talked about, that the ozone screen was established for certain by 2.4 billion years ago, although there may have been shielding before that from the organic haze. And as I said at the outset, some organisms, the mat formers, may not have cared about the UV screen. There's more to the oxygen story, which I don't have time to go through, but we talked about it a little earlier in the week. There's a lot of evidence, sort of more indirect evidence, that oxygen went up for a second time at the end of the Proterozoic, up from, say, 10% of present values up to close to its present value. And that's a pretty good, reason. Well, that's one of the reasons why multicellularity may have been invented at that time and why you get the Cambrian explosion when it did occur. So let me pause there and see if there are questions on that part. Yes?
Not quite this part, but earlier you showed a graph that there was a lot of nitrogen in the atmosphere. Can you say where it comes from?
Yeah, so nitrogen, that's a good question because I haven't talked about nitrogen. Nitrogen comes in, maybe Jonathan, is Jonathan in the back there? Jonathan hopefully will talk about it. We think that most of the nitrogen comes in the organic compounds. It's bound to organics in the meteorites. And so, at least my understanding of it is that it comes in with carbonaceous chondrites. And there's a lot of nitrogen that comes in. One way of looking at it is you look at Venus. Venus has about 3.5% nitrogen in its atmosphere, and that's a 100-bar atmosphere. So Venus actually has about 3 times as much nitrogen in its atmosphere as Earth does in its atmosphere. And that's kind of curious because Venus and Earth have about the same amount of carbon. Venus has CO2 in its atmosphere, and Earth, we heard from Jonathan this morning that it's mostly in carbonates and also in kerogen. So it makes it look as though Earth probably has more nitrogen than is present in the atmosphere. And if anything, you go back into the Archean, there may have been more N2 in the atmosphere than there is now. Some of it has been removed over time by being incorporated into organic material, and then some of that organic material gets buried and actually gets subducted into the mantle. So Colin Goldblatt, who was at University of Washington until just recently, he and Kevin Zonley have a paper that came out within the last year or two arguing that, back in the Archean, the N2 partial pressure was 2 or 3 times higher than it is today. And that may be right. It actually gives you a little bit of, gives you 4 or 5 degrees of extra warming, not because N2 is a greenhouse gas, but because that pressure broadens the absorption by water and CO2. And so, I think that's a long-winded answer, but there was probably nitrogen around very early, maybe a lot of it. Yes, Elaine?
I think it's worth mentioning that maybe the second rise of oxygen has triggered the Cambrian explosion. But as you probably know, there have been recently, 2 years ago, the discovery in the Gabon in Africa of fossils that looks like pluricellular object, living system, and those were at 2.2 gigayear.
Multicellular life? So I'm not sure I heard all of that question.
No, what I wanted to say, I wanted to stress that there has been recently a discovery of fossils that looks like pluricellular species between eukaryote and pluricellular, and those are at 2.2 gigayear ago, which could have been the same explanation that.
Oh, right.
Was a Cambrian explosion.
Right, but the oxygen requirements of eukaryotes, if you just have small eukaryotes, single-celled, they can get by fine at 1% of present oxygen. Do you know
Some are totally anaerobic.
So these small eukaryotes don't need much oxygen. They're much more sensitive to UV than prokaryotes are. And so
the one they are talking about are big animals, several centimeters. Yeah.
Okay, I'm not sure I know this report. There's that fossil that Bruce Runniger reported, Gripania, right? That there's some big sort of semicircular things which were once claimed to be eukaryotes back at 2 billion years ago. But I don't know this report that you're referring to.
For eukaryotes, one of the biggest and most important biosignatures is steroids. And finding some of essentially they are modifications of cholesterol, they're ring structures, and so while all the absolute ring structure is very, very stable. And so they've seen these sort of steroidal things out into about 2.7, actually. So you're right in that respect that, eukaryotes are probably in that age group. Now, that doesn't mean that they were multicellular, however.
Yeah.
There is a debate on that looks rather probable.
Okay. Yeah, you need some real paleontologist here to comment critically on that claim. There's all sorts of discussion as to when multicellular animals arrived in the record. I have a colleague at Penn State, Blair Hedges, who does molecular phylogeny, and he tries to do what are called molecular clocks, looking at the DNA and figuring out from the DNA when multicellular organisms evolved. And he would say back well into the Proterozoic, well before the Cambrian. But on the other hand, the paleontologists that look at fossils are very skeptical of that because they say if those things were there, why don't we find them in the fossil record?
We found them.
Well, sometimes people find things and then other paleontologists don't agree. So it's very, very difficult to tell with these small little fossils. That's why, the most famous debate recently in microfossils was between Bill Schopf, whose name I mentioned, and Martin Brazier in England, and it had to do with cyanobacteria. So Bill had claimed not just that these stromatolites in Warrawoona were cyanobacteria, but he had microfossils from Warrawoona that he says he didn't claim they were cyanobacteria, but he certainly implied that they were cyanobacteria. And Martin Brazier was writing a book on early life, and he went and went to the Royal Museum in London, which actually had all these samples, and he took them out of the collections and he put them under and looked at them through a confocal electron microscope, which uses lasers and allows you to get 3D definition in there. And then Brazier published this, he thinks they are not even fossils at all, not cyanobacteria, but not even alive. They're just blobs of carbon in there. Graphite. And, I think Brazier won that debate in my opinion.
There's at least 2 other papers that have come out substantiating that they're graphite. It's really interesting to look at the Warrawoona. What they actually did is they looked at those structures that Bill Schopf thought were cyanobacteria, and they're filamentous. But as you go deeper down into the actual sample, you see it tapering off and doing weird things like graphite does.
Right.
So it's as if Schopf actually took only that portion of the sample that actually, you can make a strong case for that they look like oscillatoria.
Yeah, now that that's come up, I'll stick a slide of that in my talk next time so we can look at that.
I'll make a point. It's a phrase I love to use as a microbiologist that a lot of sometimes paleo and other people use, which I call buzzomorphizing. So you see a structure of some kind of fossil, and you immediately relate it to some organism that's living today. To me, that's bugomorphizing, which could really get you in trouble. So anyway, new term. Okay.
All right, so now I'm going to get away from microfossils where you can actually get in a lot of trouble real quickly. And I'm going to talk about hydrogen escape, which is a much less controversial subject. But it's actually very important to this group here, which is why I stuck this talk in here, talk and a half now. And so I want to try to motivate this before I get going on it, because I know some of you are wondering why do we want to study hydrogen escape? Well, it's very important for understanding not just the evolution of the Earth, but also for understanding exoplanets. If we see a planet out there that has, let's say it has a signature of oxygen or ozone in its atmosphere, like we were just looking at, is that really evidence for life or not? And my claim is that if you don't understand hydrogen escape, you cannot make that distinction, because if you don't understand hydrogen escape, you won't know how much oxygen was present prior to the origin of photosynthesis. And I'm going to back that claim up by showing you 3 or 4 mistaken attempts to derive the prebiotic O2 level. It was not understood for a long time. And in case I forget, the person who actually solved this problem, I've mentioned his name already, was Jim Walker. He's JCG Walker in the literature. He was on my thesis committee, and he wrote a book in 1977 called Evolution of the Atmosphere, which came out, he had given me an advance copy actually when I was working on my PhD thesis. But everybody up until Walker did this problem wrong, and then Walker figured out how to do it right. And I'm going to describe basically how that problem works. So here's one of the wrong attempts on figuring out prebiotic oxygen. These were a series of papers by Berkner and Marshall back in the 1960s. Berkner and Marshall were atmospheric scientists, and even though they did the problem wrong, I found the papers fascinating. This is what got me interested in the whole ball game in the first place, because they were exploring the connection between oxygen and ozone and early life, and at least attempting to do that in a quantitative manner. So what they realized, which was correct, is that if you think about, let's forget about photosynthesis now and just say, what's the net source of oxygen? Well, the only net source of oxygen on the early Earth is photolysis of water vapor followed by escape of hydrogen to space. Now that may confuse you, because I showed you in my last talk that you can get oxygen from CO2 photolysis. But think about that. You photolize CO2 and make CO and O, and then the O's recombine to give you O2. But unless you get rid of something, then the CO is going to recombine with oxygen down in the lower atmosphere. And so that's a transient source of oxygen. That gives you oxygen at high altitudes, but that can't cause oxygen to build up at low altitudes. So in order to get oxygen to build up in the atmosphere, you have to have a leak in a cycle. And I should have put in a slide, but think about the organic carbon cycle that I talked about a couple days ago. That's the one that produces oxygen. Well, that one wouldn't give us any oxygen either if that cycle didn't leak. Because if you just had photosynthesis going in one direction and respiration and decay going in the other direction, that would be exactly balanced and there would be no net oxygen production. But the reason that cycle does give us oxygen is because some of that organic matter leaks out of the cycle. It gets buried in sediments, and then it becomes incorporated in rocks eventually and becomes this kerogen, or becomes fossil fuels. So it's that small leak in the organic carbon cycle today that gives us oxygen from photosynthesis. Similarly here, on the prebiotic Earth, the only way that you really get a net source of oxygen is to have a leak you have to leak hydrogen out to space, because then the oxygen that was in that water, which is where the hydrogen started out from, that can combine and give you free O2. All right? So this is what Berkner and Marshall realized. But then the part that was wrong was they sort of did the problem in their heads in a way, and then they did some numbers on it, and they said, okay, well, when is that leak to space going to stop? And they said, well, it's going to stop when you build up enough oxygen that will shield the water vapor from photolysis. Because for the hydrogen to escape, you have to photolize the water vapor with UV radiation. And so in Berkner and Marshall's models, you build up O2 until it shields the water vapor. And let's see, this plot here, you don't have to read these graphs. They're hard to read because of the fonts that were used. This is the thickness of O2 required to absorb UV to extinction. And then there's here's a plot that you can read. This, I read those papers in graduate school, and then I worked on this problem for my PhD thesis. So I replotted the absorption coefficients of oxygen and water and CO2 here in the UV from about 120 nanometers to 220. And notice that oxygen has it's got a continuum down here, which is called the Schumann-Runge continuum, and then it's got these Schumann-Runge bands, which are vibration-rotation bands superimposed on the electronic transitions. Water absorbs right here. It's got continuum absorption, and CO2 also has continuum absorption. It's a little bit less effective of an absorber. And so you can see that if you build up enough oxygen, you could shield the water vapor from photolysis. So that much is right. Now here's the other invisible plot from Berkner and Marshall's paper. And this is the one where they actually calculated their result. The result that they got, and I'm not going to try to go through the axes there because you can't see them. The result that they got is that oxygen would build up until it was somewhere between 10 to the minus 3 and 10 to the minus 4 PAL, which doesn't sound like a lot of oxygen, but that actually is a lot. That's a very oxidizing atmosphere. And that would be, for instance, really bad for theories of the origin of life that happen at the surface. It might not affect theories of the origin of life that happen at hydrothermal vents, but it would kill off Miller-Urey type synthesis for sure. And as I pointed out on the slide, this conclusion is wrong. It's not as wrong, though, as the next model that came out. The next model was done by a guy named Brinkman, published in 1971, and he predicted that prebiotic oxygen, abiotic oxygen, could get as high as 0.27 PAL of O2, a third of what it is today. So how did Brinkman reach this astonishing conclusion? He looked at the sinks for O2 and the sources for O2, and for the sinks of O2, he included a sink due to crustal oxidation, oxidizing iron in the Earth's crust, but he neglected the volcanic outgassing of hydrogen and other reduced gases, which is actually in Jim Walker's model, and in mine, that's what actually keeps oxygen down to low levels. And then for the source of O2, this is coming from water vapor photolysis followed by hydrogen escape. He just picked a number out of the air and he assumed that 1/10 of the H atoms produced by H2O photolysis escaped to space. He just pulled that number right out of the blue and stuck it in his model. That gives you an enormous source of oxygen, because if you don't have a UV screen, then that UV is coming in and there's lots of water vapor in the troposphere, and it is just getting photolized like heck down there. So Brinkman got this tremendous source of O2. We didn't have enough sink, and so we got way too much oxygen. So then in 1973, I keep coming back to Titan because a lot of things that are important for the early Earth, the evolution of the Earth's atmosphere, we've learned from studies of Titan. Jonathan's raising his hand back there, yay, because Jonathan likes Titan. So there was another atmospheric scientist, Don Hunton, who I'm sure Jonathan knows. Don Hunton was working on Titan, and he was trying to understand how hydrogen escapes from Titan. Because Titan has this nitrogen methane atmosphere, and you produce hydrogen, and Titan is losing hydrogen to space. And actually, I don't know, Jonathan, whether you'll talk about it or not, but the methane is polymerizing and giving ethane and forming higher hydrocarbons in Titan's atmosphere. So Hunton was interested in this same problem, and he actually worked out the mathematics of how hydrogen escapes from Titan, which happens to be the same way that hydrogen escapes from the Earth.
Juan paid my salary for a year when I first came to Arizona.
Okay.
So I actually worked for him.
All right.
But not on this problem. That was long after.
Okay. Well, I said Jim Walker figured this out. Jim Walker picked up on what Don Hunton had done, and that's how we think we understand hydrogen escape today. Okay. Now I'm going to keep an eye on my watch here and try not to go too long. How does hydrogen escape from the Earth today? It turns out that it can be limited at one of two places. The hydrogen escape can either be limited at the exobase around 500 kilometers or the homopause around 100 kilometers. And these are terms that only aeronomers, atmospheric scientists who study the upper atmosphere, necessarily know. But the exobase is the altitude at which the atmosphere becomes collisionless. And you can define an exobase by setting the mean free path of molecules equal to the local scale height. It's kind of crude, but it doesn't actually matter exactly where you define it. And so mathematically, that's 1 over sigma n is kT over mg. And you solve for the number density, and you get something like 4 times 10 to the 7th molecules per cubic centimeter. So that's the point where, if you have a molecule, as I'll go through, if a molecule is headed upwards with more than the escape velocity, then it's not going to bump into another molecule, and it can just take off to space. So that one is actually the one that's more obvious. This is the one that's less obvious, and this is what Don Hunton figured out when he was studying Titan. The homopause is this region in Earth's atmosphere. It's about 100 kilometers up, and that is where the heavy gases, the light gases, start to separate out from the heavy gases. So why is that? In the lower atmosphere, all the way up to about 100 kilometers, the atmosphere is mixed by what we like to call eddy diffusion, but it's mixed by turbulent eddies and winds, large-scale winds. There's all sorts of mass motions going around. And you know this because it's relevant to the ozone problem again. Ozone in today's atmosphere was getting destroyed by freons, which are actually very heavy gases. And the skeptics, there were skeptics on ozone depletion too for a while. The skeptics said, well, freons couldn't possibly be destroying the ozone layer because they're heavier than air and they would never make it up into the stratosphere. That's wrong because the atmosphere is well mixed up to about 100 kilometers. Now when you get up to 100 kilometers though, then the strength of these eddies, well, it stays, it doesn't actually decrease, but molecular diffusion is increasing, and molecular diffusion increases very fast because it's proportional to 1 over the density. So, and so then what Hunton showed, which I'm not going to go through the whole math, but I'll give you the result, is that the escape of hydrogen from Earth today and also from Titan is limited by the rate at which hydrogen can diffuse through the homopause. So what does that mean physically? The atmosphere, Earth's atmosphere is mostly nitrogen and oxygen, and those are heavy gases that are not escaping. So they're in hydrostatic equilibrium. The hydrogen is going out the top, and so the hydrogen has to slowly diffuse upward through the static background gas in order to get up there. And there's a constriction right at the homopause where the diffusion rate is the most limiting, and that leads to what's called the diffusion limited escape rate of hydrogen. This was Hunton's big discovery back in the early 1970s. Here's a very scrappy diagram. I need to sit down and actually spend some time making figures, but this shows what happens if you model things in terms of a diffusion coefficient versus altitude. K is what we call the eddy diffusion coefficient. That's parameterizing these large-scale motions and turbulence. And K is actually pretty high down in the troposphere because the troposphere is convective. You've got weather activity. And then it goes through a minimum in the lower stratosphere. The stratosphere is stratified. That's where the name comes from. And then K increases again as you go up higher in the atmosphere, and that's because of the breaking of gravity waves. And I'll always have to pause when I say that to astronomers, because astronomers think of gravity waves as these things that are generated by dying pairs of neutron stars. For an atmospheric scientist, a gravity wave is a wave in the atmosphere where the restoring force is gravity. And these things are generated when air, for instance, wind blows over a mountain and it gets uplifted, and then you ever see these patterns where you see 7 or 8 clouds after that. That's because the air is doing this after it goes over the mountaintop. Well, those waves propagate upward in the atmosphere and they deposit energy. They break up in the stratosphere, and that causes diffusion up there. So the eddy diffusion profile looks something like this. Molecular diffusion, that's d sub I, you can get that from the kinetic theory of gases, and it's proportional to 1 over n. The eddy diffusion is approximately proportional to 1 over the square root of n, where n is number density, and that just comes from this theory of breaking gravity waves. So these things cross somewhere around 100 kilometers or so, and that's, so up to that level, the heavy gases get mixed up, and then above that level, the light gases now assume their own scale height, and they become more abundant as you go up higher. All right, and this just says the same thing. It's just another picture that shows the homopause, and this is called the homosphere down here below 100 kilometers, and the heterosphere above that, where molecular diffusion dominates, and then this region above the exobase, where it's collisionless, is called the exosphere. All right, well, let's talk about hydrogen escape from the exobase, because either one of these can be limiting depending on what the temperature of the upper atmosphere is. Now on Earth, the upper atmosphere is rich in O2. It's not dominated by O2, but it's still got a fair amount of O2 up there. And that's a really good UV absorber. And it's also a poor IR radiator because it's not a greenhouse gas, so it can't radiate away the energy. And the Earth's atmosphere is relatively poor in CO2, which is a good IR radiator. So that means that the exosphere is hot. It's about 700 Kelvin at solar minimum when the solar activity is low, and it goes up to about 1200 Kelvin at solar maximum. And then the hydrogen, I'm going to talk about how the hydrogen gets up there, but because the upper atmosphere is hot, the H2 gets broken apart into H atoms. It reacts with hot O atoms. So there are two reactions here. H2 plus O goes to H plus OH, and then OH plus O goes to O2 plus H. And the net result is that the hydrogen up high is atomic hydrogen, which is really light. And so the atmosphere is warm and the gas is light, and so it makes the escape easy. So this is just, these are some calculations done by another former postdoc of mine, Feng Chen, where he's actually calculating temperatures as a function of altitude. And it's complicated up in the upper atmosphere because it's not in LTE. The neutrals have one temperature, and the ions have another temperature, and the electrons have yet a third temperature. So if you really want to do it carefully, you have to keep track of all of those temperatures. Now, there's three different ways that the hydrogen can get out from the top. The one that probably, at least some of you have heard of, is what's called Jeans escape or thermal escape. And that one's, I'll go through in a little detail. It's pretty easy to do. It's a classical physics calculation. That's thermal escape from the high energy tail of the velocity distribution. Then there's one called charge exchange, and there's the polar wind, which I'll mention just briefly. So to do the thermal escape, this is Jeans escape. That's a picture of Jeans. Actually, that's a picture of Maxwell, sorry. Jeans's work was based on kinetic theory. It's all part, Jeans was one of the developers of kinetic theory, but he came along after Maxwell. And here, I like this quote, this is from Jeans, the work of Maxwell is the most profound and most fruitful that physics has experienced. Oh, that's from Einstein, sorry. Physics has experienced since the time of Newton. So Einstein thought that Maxwell was a star. And you probably have gone through Maxwellian velocity distributions, maybe in some statistical physics class. So you define a distribution of atoms, f of v, which is the number of molecules with speeds between v and v plus dv. And then if you do the physics on this, which is actually pretty complicated from my standpoint, you can derive this rather complicated looking expression, which is called a Maxwellian velocity distribution. But it looks pretty simple. It's just a hump with a high energy tail on it. And so that's all part of classical physics. Then Jeans came along, and he continued to develop the kinetic theory of gases. He wrote this book, The Dynamical Theory of Gases, in 1904. This is a kind of fuzzy picture of Jeans here. And what Jeans figured out is that if you want to look for escape up there at the exobase, then you look at a Maxwellian velocity distribution, you calculate what the escape velocity is, and then these molecules up in the high energy tail of the Maxwellian, if you're up at the exobase and these are pointed up, then those have enough energy, enough velocity to escape to space. So then these are slides I've taken from my undergraduate class, and I asked them, how do you do this? You have to equate gravitational potential energy with kinetic energy. I won't ask you to do that, but you set 1/2 mv squared mv escape squared. This is how you calculate escape velocity, is equal to gmm over r, and you get the escape velocity 2gm over r to the 1/2, which if you evaluate it at 500 kilometers for Earth is a little less than 11 kilometers per second, a little lower than it is at the surface. So this is just saying what I already said. We now have the escape velocity. You have to then do an integration over the high energy tail to figure out how many molecules have it. And you look at you have to calculate the root mean square energy, which is 3 kT over m, square root of that. I'm going to breeze through this because I think it's boring to some of you. The most probable velocity is square root of 2 kT over m. If you evaluate these for atomic hydrogen at 1,000 K, the most probable velocity is 4 kilometers per second, which is less than the escape velocity of about 11 kilometers per second. So most of the hydrogen doesn't escape, it's just the high energy tail. But they're not too different. And then what Jeans did is he defined this escape parameter, lambda c, as the ratio of gravitational potential energy to thermal energy at the critical level, which is the exobase, gmm over rc divided by 1/2 m v sound squared, and you get lambda c is gmm over ktrc. That's called the Jeans parameter. And if that Jeans parameter is small, then escape works. If the Jeans parameter is large, then it doesn't. Now, so I'm almost done here. Maybe I'll just give the Jeans escape flux and then quit. So if you then do this integration that I mentioned over that high energy tail and put in the geometry, you derive this slightly fuzzy formula in this slide. It's really simple. It's just the Jeans escape flux is a product of the number density of hydrogen at the exobase times this isothermal sound speed, and then there's an exponential of the Jeans parameter. And there's a 1 plus lambda c. So I'm out of time for today. Next time I'll finish off hydrogen escape at the top, and I'll go through the diffusion limited flux and then try to show why that's useful in calculating these early oxygen levels. Thank you. Yes?
What if you have a dry stratosphere? How do you get the water, the hydrogen source, to the...
Yeah, so that's the part I didn't get to today. So the trick then is to get water up in the stratosphere. The diffusion, just to anticipate what I'll do tomorrow, the diffusion limited rate is proportional to the total amount of hydrogen in the stratosphere in any chemical form. And so water is not up in the stratosphere. There's a little bit of water, a few parts per million, but that's why Brinkman was wrong, because the amount of water, it's only the water in the stratosphere that leads to escape. All that water that's down there in the troposphere below what we call the cold trap does not lead to escape, even if you're photolyzing it very quickly. So the hydrogen that's produced in the stratosphere, it's coming from two regions. It's coming from water at the tropopause and methane at the tropopause, and they contribute about equally to the present hydrogen escape rate. Yep.
Shouldn't there be one time scale on which you lose all your hydrogen. So isn't that the critical thing that matters when you consider?
Yeah, so that's a good question. So if the temperature is high up at the exobase, then genes escape is very efficient, and so you start to lose hydrogen very rapidly. And as you said, you have to replenish it from below. The rate at which it can be replenished from below is the rate at which it can diffuse upward through the homopause. See? And so that's why we get diffusion-limited escape on Earth, because escape from the exobase is efficient. On Mars and Venus, the exospheres are cold because they're CO2 dominated, and so the escape rates are controlled by escape conditions at the exobase and not by conditions at the homopause. Okay, so thank you.